Hello, my name is Matthew, and I have the privilege of being paid by Ericsson to make the world a better place through open source, and for that I am grateful. I would like to show, to celebrate Trace Compass 10, an interesting unbalanced load. This is a benchmark that I wrote, and it didn't give very interesting results, and I was trying to figure out what was happening. But of course, this is Trace Compass 10's release, so let's try something a little different. You can see here the keys are going to be monitored down here, but let's use the Eclipse Theia based or VS Code extension version of Trace Compass to figure out what's going on. I'm extending this view so that we can see all of our states, and the program itself is relatively simple. In fact, I will just pop it up very shortly. It is right here. So you see we compute the sum of squares, and honestly this is just doing work for work's sake. You can see that we have a bunch of workers that will be running. So you have work, and work will create a thread, and then at the end it will join once it's done. Now back to the trace. If you look here, you can see that you have one thread working, then you have two threads, then you have three, and so on and so forth. It's rather hard to understand, but of course we can just select a better source. Let's look at CPU usage. And this is CPU usage in the overview, which I consider to be incredibly cool. You look at the axis here, you're at 200. It's going to keep running. I'm pretty sure this is the first run, second run. And then we're going to have the third run, fourth run, fifth run, sixth, seventh, and there should be 8th all the way to 16. This is much more significant in terms of information than what we have with our events density view for this given problem. So you look at your first run here, and you can see the runtime here, which is down here. Same for the second run. Same for the third. Now you'll notice that the third has a little step, and the fourth has a larger step. And it's rather hard to figure out what's going on here. So we're going to go back to Trace, and instead of looking at our resources view, we're going to look at our thread status. So I am making this guy smaller, making this guy bigger. Then we're going to scroll down a bit to find the threads in action. There we go, sum of squares. When we look at this, it becomes pretty obvious what happened. We had a workload, and the workload was not necessarily balanced. And since we had joins, we basically were taking the longest executing element of the workload. For example, here and here and here. And what becomes very interesting is when we scroll down, you can see that once we have a number of jobs that are greater than the number of threads, we can actually have some pretty interesting effects where the jobs are small enough to start getting partitioned properly, and that's when we start reaching our theoretical maximum of calculation. But when we calculate our time here, and I'm going to zoom in so that we can see what's going on, you can see there's a lot of orange. Orange means that your CPU is being held by something else, or you are, but the thread is not aware of this, which means that since we have our benchmark, which starts our timer here and ends it on the join, obviously we end up with a longer self time than what is actually given on the CPU. This is showing a double inaccuracy on our benchmark. First, the ends are jagged. The ends are jagged because the workload is poorly allocated. And secondly, we don't record when we are scheduled out. This is very evident when you have kernel level tracing, like the ones we have from lttng, and when you have a good tool like Eclipse Trace Compass to visualize it, or of course the Theia and or VS Code plugins for Eclipse Trace Compass so that you can visualize it in your more modern IDEs. I hope this is useful. I hope that all problems become evident when you look at them properly, and I wish you some happy troubleshooting. Thank you.